Positions and vectors in 1D. Positions are locations of points somewhere in space, and they're specified mathematically by coordinates in a coordinate system. In 1D, we're mainly going to be using Cartesian or rectangular coordinates from a specified origin point. For example, let's think about the point P. So here's P. It's located at this location. Everybody can see where it is. It has a position, even before we've talked about coordinate systems. But if we want to say where it is, we need a coordinate system. So let's add a coordinate system here. We'll add an x coordinate, and here's a specified origin. And assuming we mark some ticks on this x coordinate, so we know how long different distances are, now we can clearly say that P is at the position with coordinates x equals 3 meters in this coordinate system. If we take another point, Q sitting out here to the left of the origin, then we can say that Q is at the point with coordinates x equals -2 meters. Note that x as a measurement does not have units. Instead, values have units. So in this case, we can say that x equals 3 meters, or we can say x equals 300 centimeters, or we can say that x equals 9.8 feet, and these are all in fact describing the same position in this coordinate system. We shouldn't say things like x is measured in meters. We also shouldn't say things like x equals 4 without any particular unit attached to it. Turning now to vectors, so we're going to use vectors to describe forces, velocities, accelerations, all sorts of other things. Vectors are objects that have a magnitude and a direction, but don't have a position. So some authors call this a free vector in textbooks. Let's draw a vector here. Here's a little orange vector. We're going to label this with F. We'll always draw little arrows over the top of vectors to indicate that it's a vector and not a scalar. So this might be a force, for example, a force F. In this case, we could say that F, the vector, equals 3 newtons acting to the right, in the rightwards direction. We can take F here and we can move it around. So here's F again. Here's also another F. These are all the same vector F. These are not just different vectors that are equal to F. They're really the same thing. We just drew it in a different place. The magnitude of a vector is a positive scalar, and it's just the length of the vector, ignoring direction. In this case, we'll write F, and we'll leave off the arrow to denote magnitude always. So if we've got the vector F with an arrow over it, we write just plain F. That means the magnitude of the vector F. In this case, F is equal to 3 newtons. Again, only values have units, not the vectors. So we can, or the magnitudes. So 3 newtons is the same thing as 0.62 pound force. And it doesn't matter which of these things we write, this is still the same magnitude F. Vectors are commonly written as a combination of basis vectors if we want to actually describe what the vector is. Another common way to describe a vector mathematically is to write it as a combination of basis vectors. So in 1D, I hat is the basis vector in the positive x direction, so that's generally going to be to the right. Let's draw I hat here. Let's also redraw F. And so here we can see that F is in the same direction as I hat, but it's longer. And so we can say here that F is equal to 3 newtons in the I hat direction. The 3 newton part of that expression is the component of F in the x direction. Note that basis vectors don't have units. Instead, it's the component values that have units. So if we rewrite the vector F, we can write F is equal to the component Fx, the amount of F in the x direction, times I hat. And here Fx will be equal to 3 newtons. And it's the value 3 newtons that has the units associated with it, not I hat and also not Fx itself. So I hat here is an example of a unit vector. And unit vectors just capture the notion of direction without any particular magnitude. Sometimes we say that I hat has magnitude 1 with no units, or sometimes you could also say that it just doesn't have any particular length at all. So if we take any vector, we can normalize it by its magnitude to obtain a unit vector in that direction. And we're going to denote that with an over hat. So the I hat we saw before, the hat just here means unit vector. So f hat here is going to be equal to the vector f divided by the magnitude, the length of f. So in this case, that's 3 newtons in the I hat direction is f, divided by 3 newtons. We can see that cancels, and we're left just with I hat. So we know that the unit vector in the direction of f is in fact I hat, which we already knew just by looking at it. And we can draw that over here. Take another example. Suppose we have a velocity. So here's a velocity vector v, which is negative 2 meters per second I hat. So that means it's 2 meters per second in the leftwards direction. To find the unit vector v hat, we're going to take the vector v divided by the magnitude of the vector v. And in this case is equal to negative 2 meters per second I hat divided by the magnitude. Now the magnitude must be positive, right? It's just the length, not worrying about direction. So the magnitude is 2 meters per second. We cancel things off. We see that in fact that v hat is equal to negative I hat. If we draw that, of course, we get the idea that v hat points leftwards in the opposite direction to I hat. Observe we have two different expressions here. We can, for any vector, we can either say that the vector v is equal to vx in the I hat direction, and here vx is the component. It may be positive or negative. In this case, vx is equal to negative 2 meters per second. Or we can always say that a vector v is equal to the magnitude v times v hat, which is the direction of v. And so here v is 2 meters per second. It's the magnitude, it must be positive. And v hat is just the direction, and in this case will be equal to negative I hat.